Alright, good morning. So I'm going to be going over Coulomb's law quickly, mostly just to go over the practice questions. So my quick take on this, hopefully you've read it through, is to recall static electricity. A quick or a good video to watch would be this one. You can skip through parts. You don't have to watch it all, but that's a good warm-up on static electricity. And then what we are going through is universal gravitation. We're going to revisit this. This we should already know. We did this last unit. We have two masses. Any two masses essentially have Newton's force of gravity acted on them, depending on how far apart they are, and how massful each of them are. Okay, so you can find the force of gravity between any two objects by going the g constant, which is 6.67 times 10 to the negative 11, times the mass of the two different objects over the distance between them squared. Okay, this square on the bottom means that the distance between them is kind of more important than the mass themselves when you determine what force it will be. But that's the equation to find force of gravity between any two things. So now we'll go into Coulomb's law, which is the electric force. It turns out that you have the same type of equation. It says Fc. One problem with that is we used Fc to be centripetal force for centripetal acceleration. So we might have to change that to maybe an Fq, I guess in the future would make it more easy to see. So Fq we can say, we'll say Q means charge, the charge of something, is K, a constant, different constant than that G. The charge of one object, not the mass, the charge of the object, times the charge of the second object over the distance between them squared. So you can see it's very similar to force of gravity. And if we look, we have Q1, Q2, the charge of object 1, the charge of object 2, and the distance between them. So like in this equation, the squared means the distance between them is more important than their charge. But the charge is still important. So overall, the K constant is 8.988 times 10 to the 9. So I'm not sure what that is. I'm guessing it's 8.9 billion, and it's units, which doesn't really matter. You don't really have to remember this. Newton meter squared percent Coulomb squared. That's the constant. Now let's go through Q1. Q1 is the charge of an object. So it just means the charge of the object. And what is charge? Charge is pretty much the negative or the positive thing on an object. It's hard to describe actually what charge is. It usually has something to do with electrons or lack of electrons. So it goes down to the atomic scale. So if something's overall negative, it has more electrons than protons. If it's overall positive, it has more protons than electrons. So that's generally what charge is. And then R is just the distance between them, but the distance from where? Their centers? Not quite. Their center of charge, wherever that be. Okay. Usually it is the center of the objects, especially in our questions we're going to do after. All right. So now we go, what is a Coulomb? Coulomb is this new unit that represents charge, okay? Because if you have more electrons than protons, you know it's going to be negative, but you need a number to quantify that. So what they say is we're going to create this unit that quantifies it called 1 Coulomb, and it's a charge 6.2422 times 10 to the 18 electrons, okay? So if you have that many more, which is a lot of electrons, more than a billion, more than a trillion, that'll equal 1 Coulomb. So you can estimate that 1 Coulomb is a lot of charge. Okay, you have a lot more electrons than protons in this thing. Okay, so this is a lot of electrons, a lot of charge. Usually we actually deal with microcoulombs or smaller amounts, but this is the unit that they made up. So that's the unit. The main unit is a Coulomb. Okay. And then they have this other thing called an elementary charge, which is a much smaller quantity of charge, or of charge. It ends up being the charge of 1 electron. Okay, so this is the charge. 1 Coulomb is the charge of that many electrons, but 1 elementary charge is the charge of just 1 electron. So you can see, if you want to get it in terms of coulombs, you just go 1 divided by this, or just this. It is 1.602 times 10 to the negative 19 coulombs. Okay, so you can see that 1 electron is a very small proportion of 1 coulomb. So here's a video that you can watch. It's somebody going through kind of experiments to see how they came up with this a bit. So I would recommend looking at that. So the rest of the time is just to work on practice on how you kind of apply this. So we're going to go through I think 5 or 6 questions, and then there's practice questions afterwards to test your own skills. Okay, so here we go. What is the force that would be exerted by 1 coulomb of positive charge on a 1 coulomb negative charge that's 1 meter away? Okay, so if you picture two, usually they always have spheres. And the thing about Coulomb's law, it doesn't say anything about mass. Okay, so they don't say anything about the force of gravity. So there's usually a force of charge on stuff and also the force of gravity. But we are just looking at force of charge generally right now. So we're going to forget about force of gravity. It's still there, but we're going to forget about it. What is the force exerted? We're going to start with our equation. Force of the charge is our K constant, Q1, Q2, over the distance between them squared. Distance between their center of charge. Okay? So this one has a 1c. This has a negative charge of 1 coulomb as well. Remember, 1 coulomb's huge. Generally in real life, you don't have charges of coulomb, of 1 coulomb. So we'll say this one's a positive, and this one's a negative charge. Okay, and it says they're 1 meter away. 1 meter away. Okay, so let's fill in our units. This K is 8.988 times 10 to the negative, or not negative, 10 to the 9. Okay, so a really big number. Q1 is the charge of this, which is just 1 coulomb. Q2, it's a negative charge, but what I do is I just make everything a positive charge. Even the negative ones, you just have to know that it's a negative for your end answer. So we have a plus and a minus. All over the distance between them squared, which is 1 squared. 1 meter, right? The distance between them is always in meters. So then we just take our calculator, 8.988 times 10 to the 9 times 1 divided by 1, which is just 8.988 times 10 to the 9. And what unit do I put here? It's a force, so I have to put newtons. Okay, so overall, that's that. Force is generally, usually we don't do this, but force generally is a vector, which means it has a direction. So what force to be exerted by a 1 positive charge on the negative charge? Okay, so if you look at the negative charge, since it's positive and negative, you know it's going to go that way because they're attracted when they're opposite charged. Okay, so that means this will want to go towards that one, so it'll be a force to the left. Okay, that's why I didn't put the negative sign up there. I just decided to take a look at my picture and I knew it was going left. Okay, because sometimes the negative signs can confuse you. And that's that there. And then this is around 9 billion newtons. So you can tell if they were both 1 coulomb in charge, 1 meter away, or pretty far away, that's a lot of newtons. That's a lot of force. Okay, so you could picture them attracting at a very fast speed if you could reach those high coulomb amounts. Next one, a small sphere with a charge of 3 microcoulombs is brought near another metal charge of 2.1 microcoulombs. The distance between the two spheres is 3.7 centimeters. Okay, so you have your two spheres. You have 3.7 centimeters. One's 3 microcoulombs. And the other one has a 2.1 microcoulomb. They don't say what the charge is, so I'm going to assume they're the same. I'm going to assume they're both positive. Okay, so here we're going to do our same equation. FQ is KQ1 Q2 over R squared. And this is our 8.988 e to the 9. Our charge of 1 is 3 microcoulombs, which is 3 e to the negative 6. And then this is 2.1 e to the negative 6 all over the distance between them. Always has to be in meters, so it's going to be 0.037 meters squared. So we type that all into our calculator. One thing I do, I'm lucky with this calculator, is you can store numbers. So we always are going to use this k value. So I'm going to go ahead and go 8.988 e to the 9. I'm going to enter. So that's the 9 billion. And I'm going to hit store down here. Store. And I'm going to hit alpha. You can choose any letter to store it in. Alpha, I'm going to store it in the letter K because that makes sense. So that means every time I hit alpha K, it's going to be that number. So I don't have to type that in every time. Alright, so I have K times 3 e to the negative 6 times 2.1 e to the negative 6. I'm going to enter, divided by 0.037 squared. So we get a 41.4 Newton value. And those are tiny charges compared to the 1. So it makes sense that those are more kind of real world microcoulombs, kind of that dimension they work in. So that's the force that they both kind of feel on each other, 41.4 newtons. Number 3, what is the distance between two charges, those two charges, that experience a force of that? So I'm going to start with my equation. Okay, and then this time they give you the force that's being exerted, 240 newtons. So we're going to fill that in, 240. I'm going to just write K. We know that's the 8.988 times 10 to the 9. Charge 1 is 8 e to the negative 5 and 3 e to the negative 5. And then R we don't know, so we leave it as R squared. We got to solve for R, so let's divide by K, this, and this. Nope, sorry, I don't know what I was thinking. Divide by, or multiply by R squared and divide by 240. So we'll get R squared equals K e to the negative 5, 3 e to the negative 5 over 240, and then we take the square root of that. So we end up with, when we type it in, I end up with a 0.30 meters, or 30 centimeters. Okay? Alright, so that's kind of the main way to use those equations. And now we're going to look at 3 charges. So what happens when you have more than 2 acting on each other? You know there's a force. If they each have charge, you know there's a force acting on each of them. A on B, A on C. You know there's a B on C, and there's also a B on, or that's all of them. So 3 tiny spheres are lined up. The first and third spheres are 4 centimeters apart. So that's going to be 2, and that's going to be 2. Q of A has 2 e to the negative 6 charge, or coulombs. QC has 1.5 e to the negative 6 coulombs. And then they put the second one really quickly in between them, and has a charge of negative. So this one's going to be positive, negative of 2.2 e to the negative 6. Alright, so what is the net force on sphere B? So you know there's a force. It's going to be a traction between those two. So it's going to, the A is going to make the B want to go that way. And then C is positive as well, so that's going to be a traction. So it's going to, C is going to make B want to go that way. So overall there's two forces. One going left, one going right. Let's find the left one. Okay. So the left one, which is the force charge of A and B, is going to be K, Q1, Q2 over R squared, which is K. Our Q1 is 2e to the negative 6. This one is 2.2 e to the negative 6. And then the difference between them is 0.02 meters squared. So let's type that all in our calculator, and I get 98.9 newtons. Remember, it's the left. And then we're going to do the other one, the right one, which is the force of charge of B and C, K, Q1, Q2 over R squared. And we get a K. We have 1.5 e to the negative 6. Note you could write this one first. It doesn't really matter. 2 to the e to the negative 6. And the difference between them, again, is 2 centimeters squared. And the number I get for that is 74.2 newtons. So this number is bigger than that number, so it's pulling to the left more than it's pulling to the right. The reason why is because those two numbers are bigger. Those two numbers together are smaller. So one thing to mention is A is pulling B to the left and C is pulling B to the right. But in reality, also B is acting on C, causing it to go that way and A to go that way. Okay. But they're just asking you about B. That's why we're only looking at B. So overall, we know it's going to end up going left, but how much? So the net is going to be kind of the 98.9 minus the 74.2, which is 24.7 newtons. And since this is a vector, you kind of need a direction to the left. All right. All right. So now that's done, and we have only one question left. This one's kind of a doozy. So there are three spheres. Charge of A is negative 3.3 e to the negative 6. B is that. And this, we'll say, is C. That's a typo. Is 2.2 e to the negative 6. Calculate the net force on each sphere. Okay. So you can kind of expect a triangle happening here. This difference between A and B is 3 centimeters. Difference between B and C is 1.5. So let's find the forces of each of these. Okay, there's going to be a force here, A and B. There's going to be a force here, A and C. There's going to be a force here, B and C. Okay, so force of A and C is going to be our K, Q1, Q2 over R squared. So you're going to put in the charge of A, which is it's going to be a K, and then 3.3 e to the negative 6. Charge Q2 is going to be 2.2 e to the negative 6 all over R squared, which is the distance between them. But what is the distance? They don't give us that. We have to use Pythagoras. So we get a 1.5. We get a 3 centimeters. So overall, if we use Pythagoras, it's square root of 1.5 squared plus 3 squared, which is plus 3 squared. 3.354 centimeters. Okay, so that means that my R is 0.03354 squared. So overall, my FAC is going to be K times 3.3 e to the negative 6 times 2.2 e to the negative 6 divided by that 0.03354 squared. So I get 58.0 newtons. Okay, and I can do the same process, the same thing, with the different charges for each one to get A, B, and BC. So I'm just going to write them here. I'm not going to do the work there in this video. So we have A and B here. If we take that charge and the distance between them, which is 0.03 meters, we can end up getting 65.9 newtons. And then we can also do force of B and C, which using those two charges and the distance between them, which is 0.015 meters, will give me the biggest amount, 175.8 newtons. Okay, one thing to notice is A is a negative, B is a positive, and C is a positive. So you know that this one's going to get attracted to both of those. Those two are going to get repelled from each other. And that is going to be attracted to that, that one attracted to that. So they're all getting multiple, oh sorry, you can see that. This one, A, is going to be negative, so it's going to be attracted to that one. A is also going to be attracted to C. B and C are going to be repelled from each other because they're the same charge. Okay, so that's what's going to happen there. We have each of our charges, 58, 65.9, and 175.8. So now we have to try to find what the net force of everything's going to be. This is where the vectors kind of come in. So let's just look at A. So this is just A, looking at A here. So if you look at the forces, it's going to be attracted to C. So let's say we have A here. It's going to be attracted kind of in that direction, and it's going to be attracted also in that direction. Okay? So if you have two vectors and you want to know the overall net vector, you have to add them together or go tip to tail. So you're going to go one here and then one here. Okay, and this is A right here. Okay, so what was this line here? This line was AB. AB. And then if there's any angled vectors, you know you're going to have to do components. Okay, so overall this is going to be, this one here is going to be AC. So this is AC in the X direction, this is AC in the Y direction. Alright, and then after you've done that, you want your net, from your start to your finish point, your net. That's your goal, is to get that net there. So let's draw it one more time. The overall big triangle is what we're going to draw. So we're going to have from there to there, and our net, because that's our end goal, is find the net force that's acting on A. So we have a net force here. We have this, which is going to be AB plus AC. We have to know what this angle here is going to be. What is that angle? That's going to be the same as this angle. And that angle is really the tan inverse of O over A, which is 1.5 over 3. So if we want to know what theta is, let's do a quick side calculation. It's tan inverse of 1.5 over 3, which is 26.6 degrees is in there. So that means this theta is 26.6 degrees. That means ACX is going to be 26.6 cosine, or sorry, it's going to be AC times cosine 26.6. And ACY is going to be AC sine 26.6. Okay, so let's write that down. ACX is going to be AC, which is 58, cosine 26.6, and ACY is 58 sine 26.6. Okay, so let's type that in our calculator. ACX is 58 cosine 26.6, which is 51.8. But we know we're going to have to add it to AB. And AB is 65.9. And we get 117.76 newtons in the x direction. And then we end up for the y, which is this part, is 58 sine 26.6. We get 25.97 newtons. So overall net, we can use Pythagoras. So it's going to be square root of our answer squared plus 117.76 squared. And we get 120.59 newtons. And usually when you're finding a net vector, you also need to find the angle. We'll call that alpha. What's alpha? It's just tan inverse of 117.76 over 25.97, which is 77.6 degrees there. Okay, so it's going to be pulled at 120.59 newtons in this direction, which is 77.6 degrees above the horizontal. And that does not make too much sense. So what? It seems too high of a value to be going up because it should be less than our original theta if that is to make any sense. So I'm wondering what I did wrong. So I think this number here I did not do quite right. So let's just relook at this number. 58 cos 26.6 plus our 65.9. Yeah, I did get that again. Oh, here's my mistake. Tan inverse is not, that's O over A, but our O is not 117, our O is that one. So I just wrote it the wrong order. So it's 25.97 over 117.76, and that should make more sense. There we go, and we get 12.45 degrees there. And that makes more sense. So when we look at it, A is going to be pulled at still 120.59 newtons, only 17 kind of in between them, at 12.45 degrees. Okay, so that is just looking at A, and that's pretty hefty. So let's look at B now. It should be a much easier one. And then C, I will just leave the answer key up in files, and I won't go over that one. So B here is going to be acted on by A and C. Okay, so B here is going to be acted sideways. It's going to want to be attracted to A, and it's going to be repelled by C. So it's going to be down by C. Okay, so then if we want to know the net force, we have to add the vectors. So it's going to be tip to tail, so there and then there. This is our starting point, this is our ending point. So we're going to draw our net or result vector there, which is our net vector. And then here, well, we're going to need to know that theta eventually, but let's just see this. This one here is going to be AB, and this one here is going to be BC. We know AB is 65.9, newtons. We know BC is 175.8 newtons. So we have those two values there. That means our net here, our net value, is going to be the square root of both of those squared. Using Pythagoras. So we take the square root, 65.9 squared plus 175.8 squared, and we get 187.75 newtons overall. But in what direction? Our theta here is going to be tan inverse of O over A. This time I'll make sure I get it right. So 175.8 divided by 65.9, and we get 69.45 degrees where I put theta. So 69.45 degrees. So overall our net vector is 187.75 newtons at an angle of 69.45 degrees, kind of downward. So let's take a look at our picture. B is going to be 69 degrees, going to go down that way initially at 69.45 degrees at a magnitude of 187 newtons there. Alright, and then the last one would be to do the same process, try to get the net force and the angle that C feels from both B and A. You're going to bet it's going to be repelled by that one, so it's going to want to go that way. And it's going to be attracted by that one, so it's going to want to go this way. So on my guess, it's going to go somewhere in between that. It's going to end up going that way at some point. Okay, but that'll be under answer key under files. Thank you.